Welcome. Good morning, everybody. In some minutes, we will start the conference. Please wait. Hello, good morning, everybody. Can you hear me?
I can hear you.
Mr. Dave, can you hear me?
Yes, I can hear you.
Okay, perfect. So let's start conference. Okay. Good morning, everybody. Welcome to the AAPG Venezuela 2020 Geodesy Conference. Let's talk about geodesy. My name is Mirel Estrada Lopez. and I am part of the AAPG UCB student chapter, and I'm pleased to do these first words before starting. We would like to thank all of you for your participation in this event organized by the AAPG UCB student chapter and AAPG Young Professionals Venezuela chapter.
I'm not hearing you. I can't hear.
Hello, can you hear me?
I can hear you, yes.
Okay, I will follow with the presentation because it's probably my friend has some internet problems. My name is Carlos Sanchez. Also, I am part of the AAPG Young Professionals, and I'm pleased to give these first words before starting. Today, we have the participation of Mr. Davud Zilkoski with the topic, the process of transitioning from a National Leveling-Derived Height System to a GNSS-Derived Height System.
I'm sorry, I had a problem with my internet. Now I'm back. I'm sorry.
No problem.
Okay.
Okay, you can follow always.
Yes, just let me.
I read the title of the presentation, but I don't have the presentation right now. If you can share your screen.
Yes. Can you see my screen?
Not yet.
Okay, just let me know. Okay.
Looks like it's
Now can you see my what?
it's just black. It says it's trying to has started screen sharing. Yeah, right now it's just all black, but
Okay. Yes, I just share. Let me know if you can see my screen. Okay. Can you see it now?
Not yet, not yet.
Just let me share it again. Okay, I'm sorry for. Okay. Okay, now can you see it?
No.
Not yet. Oh my God. Yes, it's just I'm having some troubles with the internet. I am very sorry with all. I'm just having some troubles with my internet right now, the connection. I need the screen. Please let me know if you can see it now.
not yet.
Okay. Well, in the meantime, you can see my screen. I'm going to talk again. I'm very sorry. I just had a problem with my internet connection. I'm saying my name is Mirabel Estrada Lopez, and I will welcome you, everybody here, to the conference of today. The process of transitioning from a National Leveling-Derived Height System to a GNSS-Derived Height System by Davud Zilkoski. Among our audience, we have participants from Venezuela, Peru, the United States, Mexico, Argentina, Colombia, Ecuador, Bolivia, Costa Rica, Chile, Brazil, Guatemala, Germany, and France. Now I present a brief summary about the trajectory of our guest, Davud Zilkoski, former director of NOAA's Office of National Geodetic Survey, retired, 1974 through 2009. He is CEO of Geospatial Solutions by B Z, Senior Geodetic Consultant, ESP Associates. Dave B Zilkoski received a bachelor's degree in forest engineering from the College of Environmental Science and Forestry at Syracuse University in 1974 and a master's degree in geodetic science from the Ohio State University in 1979. He was employed by National Geodetic Survey from 1974 to 2009. Mr. Zilkoski is chair of North Carolina Geodetic Survey Advisory Committee, a member of the North Carolina 2022 Reference Frame Working Group, past chair and current member of the Transportation Research Board Committee. He has authored a number of papers on GNSS-Derived Height, subsidence, surveying, and vertical datum, including a chapter in the DEM Users Manual. As guest editor of GPS World Survey, since he has authored a series of newsletters on establishing and analyzing GNSS-derived coordinates, understanding NGS hybrid and scientific models. Instruction. Before starting, I would like to ask you to disable cameras and microphones to avoid interruptions. Questions will be answered at the end of the presentation so that there are no any kind of interruptions. Recommendation, write down the questions to ask them in the space available. So now I give you permission, Mr. Dave, so you can share your screen. I'm going to stop sharing mine.
Okay, sounds good.
The conference is yours, and thank you very much for being here.
My pleasure. Gotta let me know if you can see my screen.
Yes, we can see it.
Oh, all right. So as Marie said, my name is Dave Zilkoski. I've been working in the field of geodesy for over 45 years now, mainly dealing with heights, leveling-derived heights, as well now as GNSS-derived heights, ellipsoid heights, orthometric heights, geoid heights, but that's mainly what I was interested in. I started working with the National Geodetic Survey in 1974 in the horizontal, dealing with the geometric side, and then moved over to the vertical side early in my career. So what I'm going to talk about is how the United States, the National Geodetic Survey in particular, transitioning from a leveling-derived height system to GNSS-derived height system. And I'm going to try to highlight what's important and what you need to remember. I'm not familiar with Venezuela's height system or anything, but it's very typical of what the US has, although the US is much larger. It has very similar attributes as the rest of the world. So I will go through how the major activities, there are a lot of different activities involved, but I'll go through the major activities. First, we looked at readjusting the vertical control network, and actually the National Geodetic Survey in the United States readjusted the horizontal as well as the vertical. I was the project manager for what's called the North American Vertical Datum of 1988, or NAVD88. So, but we had to readjust that in order, if you ever wanted to get to a satellite-based height system, you needed to make sure that you had a good establishing control network, vertical control network, because the users needed to transition from their vertical datum to the new datum. So that's part of what we did, and I'll talk briefly about that. We developed guidelines for going from leveling-derived heights were pretty standardized from the turn of the last century, and the procedures were pretty well adopted. But when the global navigation system came out, GPS in the United States, it was new. And so guidelines and procedures needed to be developed. So they did it for a whole geometric part of it, the latitude, the longitude, the ellipsoid height. But so you had to develop really better guidelines for people who wanted to do GNSS-derived ellipsoid heights as well as orthometric heights. And more important, they had to be consistent with the existing vertical datum, which was the NAVD88. Then finally, you have to define what the future reference frame is going to be and how it relates to the old one. So those are the three major activities that really help to transition from the National Height System leveling-derived to GNSS-derived. So first, readjustment of the United States Vertical Control Network. We prepared a special report on this. This was completed, the adjustment was completed in 1991. This report came out in 1992. There's a reference there. And by the way, I will send this presentation, or at least a PDF, to the group after I'm done. I meant to send it beforehand, but I forgot to send it through. So I will send this out. And so you'll have all of this in a PDF form. So all these references that you can go onto the website to obtain will be there. But this report talks about the results of it. I'm going to highlight a few specific aspects of it that are pertinent to transitioning. First, in the United States, from the year 1900 to the 29, there was 5 different adjustments that were performed, vertical control adjustments that were performed. And in those years, you can see the number of kilometers of leveling increased from going from a little over 21,000 points all the way up to, in the US, 75,000 kilometers. And you notice in this, in Canada, in the 1929 adjustment, the United States collaborated with Canada to do an adjustment of all of US and Canada. And I'll talk briefly about that. But what's important here is the country was expanding. City by city, roads were being built. And so in the past, the railroads were all leveled. They needed the leveling. So as the country was being expanded, especially by the roads, more and more leveling was performed. And then more and more adjustments needed to be performed to make everything consistent. What I wanted to point out here is the number of tide stations that were held. In the beginning, the first one in 1900, general adjustment, there were 5. And by the time it kept increasing until it got to the 29, which was 21. And as many people know, when you're doing a vertical datum, you usually tie it to some local mean sea level value. And in the case of large countries that border on 2 different oceans or more, you hold those tide gauges. Well, we do know that the local mean sea level established at a tide gauge doesn't truly represent equal potential surface, although back in 1900 and even 1929, it was probably much more accurate than the actual leveling data. So holding it and making it consistent was what they did. Although this did create a problem in the 29, which I will talk about. This was the leveling network used in the 29. There was 75,000 observations in the US and 31 in Canada. This is just showing the US data. Canada, up here, I don't have a diagram including it, but they had 31,000 kilometers. Basically, their primary framework went coast to coast. But what's important here, since the 29 was established using these number of tide gauges, over 1 million observations were added to the network. So 1 million observations had to be fit inside here. But you can see the tide gauges that were held. And one of the reports, when I was project manager for the North American vertical datum, I read a lot of the history of what was done in the 29 datum. And one of the things they said is constraining to some of these tide gauges made it a large issue when they had to go in and tie new leveling data, because the tide gauges weren't representative of the same equal potential surface from one station to the next. They did represent what was locally important, which is what the locals wanted. They wanted to know where local mean sea level was and all their heights relative to that, which was critical. But when you started adding all this data in, it started really distorting the network. Now, the United States would do regional adjustments as they filled in these networks where they couldn't fit them. They would go back and do large readjustments. But all of this was done by hand because none of this data was in the computer. Well, actually, back in the 29, they didn't even have today's computers. Even in the early 70s, we started looking at trying to automate the data. So that's why in the early 70s, the United States made a push to automate all of their data. They got all of their leveling data and their horizontal, both the geometric data and the leveling data. They put it all into the computer. So it's all been automated so they could do an adjustment. This is over 1 million observations were put in computer readable form. This task alone took over 10 years, a decade, to get into computer readable form. It involved more than 500,000 monuments, and there was some temporary monuments that had to be coded up. But one thing I wanted to point out is, in the NAVD88, we only constrained one tide gauge. And one of the reasons for doing that was that in the 29, when I read the material, they were saying because of all the distortions or the differences in the leveling at the tide gauges, they had trouble fitting all the data to make it conform consistently. And then a lot of the oceanographers would claim that no, the sea level is an equipotential surface. These water level, the errors in the leveling data. So there was a lot of sea surface topography effects that we're trying to estimate. And in the United States, we put out contracts and we did with Canada, worked with Canada, trying to estimate the local sea surface topography effects at the tide gauges so that we could actually constrain those tide gauges. Well, in the end, we decided that it was better to constrain one point, and it happened to be in Canada, and not constrain the other tide gauges, so that if we had to remove a systematic error from the leveling, all we worried about was the remaining errors in the leveling and not the distortion that may have been entered in by constraining to tide gauges that the actual local tide gauge measurement didn't truly represent an equipotential surface. The one important aspect that happened with the NAVD88, the NAVD88 removed all the local distortions in the network, because we now put all the data together, rejected observations that did not fit because of movement or because they were too old, and the newer observations were much better. So it became a very more consistent leveling adjustment. And it doesn't mean it was even more accurate. The relative differences didn't change that much, but the overall coast difference did, because we did not fix constraint to the tide gauges like they did in 29. So one of the important aspects is this, that the 29 had all of those distortions, and you can see the huge difference between, this is the NGVD29 data, this is the NAVD88 data, and incorporating all of this data into, all of this data inside here had to fit inside this framework. And that's why we had to redo it. But the NAVD88 removed all of the distortions. And this was extremely important for several reasons. Well, one being, when people were trying to create maps and connect from one state to the other and doing much larger projects, and then they started out in the local networks, you needed more consistent elevations. So with all the distortions that were happening in 29, NGVD29, in this network here, we removed a lot of the distortions. And there were several that were 5 to 10 centimeters between stations that were right next to each other because of the adjustments and so forth. So all of this helped to pave the way to create a new, the latest, more consistent, we believe more accurate leveling network. And it was called NAVD88, North American Vertical Datum of 88, which was the first phase of trying to create the transition to going to GNSS. and I was a project manager, and it was completed in 1991. And at the same time, I was working on procedures for doing GNSS-derived ellipsoid heights and orthometric heights, because I knew that was the future, but I knew we had to do the leveling network. So a little interesting facts about the NAVD88. I said we did the US and the Canadians combined work together. So the US network was, like I said, over 1 million observations, and the Canadian network, they did their own adjustment. We did ours separately. They had over 100,000 kilometers. We had over 1 million kilometers. And we compared at the border, at these junction points, we compared our results. And these are the differences in centimeters. So from one end of the United States all the way to the other end, we agreed with the Canadian network to better than 5 centimeters. So we knew our network was good, and we knew it was consistent, and we knew it was precise. We didn't know it was accurate because these are 2 independent adjustments. However, the leveling procedures used by the Canadians and the leveling used by the United States were almost exactly the same procedures. Very similar types of instruments, same type of instruments, same type of rods. So everything was the same. So if there was a systematic error left in the leveling in the United States, chances are there was a systematic error left in the Canadian data too. But it gave us a good feeling. We felt good about the precision. So we combined all the data and did the final adjustment to remove the differences between the 2 coasts. But when you talk about removing 5 centimeters over 5,000 kilometers, that's not very much. Now, back in the late 1980s and early 1990s, we didn't really have a lot of GNSS-derived ellipsoid heights. We did have VLBI, and so we could get the ellipsoid heights from VLBI in the newly published North American datum of 1986 adjustment, so ellipsoid height. So everything was consistent, and we had a scientific geoid that was called Geoid 90, the best at the time, although it still was not that accurate. So what we did is we compared these ellipsoid, or these VLBI-derived orthometric heights with, using this Geoid 90 with the NAVD88. And you can see that I highlighted the positive and the negative, and there was definitely differences. And actually you can pick out differences, like this is 0 to 41 centimeters, 38. So if you really look from coast to coast, the leveling derived height versus the ellipsoid derived was only different by 40, 50 centimeters. However, you get some of these outliers that are very close, that there's over 70 centimeters difference there. There's over 1 meter difference here. So it was, the accuracy of the geoid model wasn't that accurate, and compared to the coast to coast. So saying that, in 1991, NGS realized this is why we did this and made it part of our analysis, that we knew that geoid model would ultimately get better. So we knew that as it got better, we would try to incorporate it into NAVD88, and that's what we did do. My point here is that we did try to look at this because we knew that we kind of had a difference between the local mean sea level values coast to coast, but we couldn't know which one was the best. So we tried to use a different source, independent source, but because of the lack of accuracy of the geoid model, we really couldn't prove it one way or another. We believe the ellipsoid heights were pretty accurate, and good enough to be able to compare with the leveling, but the geoid model at the time still was not very good. So what does it look like today? This is using, and I'm going to explain what this is a little bit later on in the presentation, but basically this is a comparison of the latest NAVD heights with GNSS-derived orthometric heights. So in the United States, we had a program called GPS on Benchmarks, and this was encouraging users to occupy benchmarks with GPS to get a very accurate ellipsoid height on it. So we had an ellipsoid height on a benchmark, and we had the leveling-derived height. And when you take the ellipsoid height and the leveled height, you can compute a geoid height. So we did that, and I'm going to explain that a little bit later, or show diagrams. But we did that with about 32,000 stations across the lower 48 states of the United States, and took that and compared it to the latest scientific gravimetric geoid, purely gravimetric. And you can see there's this tilt, going to systematic tilt east to west. And basically it's over a meter systematic in 2020. So, but now we have a lot more data. We have a better geoid model involved, and I'll explain how that was done shortly. So we knew that we're on our way to being able to get more accurate GNSS-derived orthometric heights. And this was the first thing. So this is a good sign. Now, once we did the NAVD88 and we felt good about it, and people started using it, we said, and GPS started growing. This is back in the 90s. And it wasn't even fully functional. We started building better geoid models. We said people want to use the GNSS system to get the heights because leveling is so expensive. So we started looking at guidelines, figuring out how do we develop good guidelines for users, surveyors, to be able to go out, use the new satellite system to estimate geoid heights or ellipsoid heights to get better orthometric heights. And this is a standard formula where if you want an ellipsoid height, it's equal to an orthometric height plus the geoid height. So in the past, you did the orthometric height by leveling, the geoid height you did by modeling, and you got the standard picture that talks about the geoid height, the ellipsoid height, and the orthometric height, and how they're related. So this was, we're looking at, say, well, we have to be able to develop a lot of good guidelines. We have guidelines for orthometric height for leveling. They were pretty well documented. So we need guidelines for how would you get accurate ellipsoid heights. And the reason being for trying to get accurate ellipsoid height, because we wanted to turn the equation around. Now we wanted to get, instead of ellipsoid heights, now we want to get orthometric heights derived using the satellites. So we get ellipsoid heights from the GNSS, and that's a straight ellipsoid heights coming from it, and then the geoid height. And this, obviously, the equation, you just change it around. You get the ellipsoid height minus the geoid height, gives you the orthometric height. This was the goal, but you have to devise guidelines. How do you get accurate ellipsoid heights so that they're consistent with the NAVD88? And then how accurate is your geoid model? And that's where we were trying to obtain and improve the geoid model. So this is very simple, same diagram, just trying to show the equations and what you have, the orthometric height, which is perpendicular to the geoid model, the ellipsoid height, perpendicular to the ellipsoid, the difference between those deals with the geoid height. And it's the same equation, very simple equation. And I always like to note out that it's basically an approximation because these two lines are not parallel. So there is a deflection, which we all know about. But for all practical purposes, it's small. Maybe in the future and some applications, it's going to be more important. And that I'll leave to the next generation of geodesists to really improve. But I'm highlighting this geoid because the geoid is the critical part of what we have left. And we knew we had good orthometric heights from the NAVD88. We started getting good ellipsoid heights with better satellites up there, more satellites, better procedures, better algorithms, better antennas. All of those factors came into it. So when I talk to surveyors, it's very important about doing good surveying practices and following guidelines. And so that was one of the things that when we were trying to transition, we had a lot of people just going out there doing whatever they wanted. So in good surveying practices, you needed to be able to develop better practices. So the National Geodetic Survey, and I was a lead player in doing this, we developed these guidelines and we document them. And this is a key point. All these things are documented so that the user can go out and undertake this, and everybody, so if they want to follow certain guidelines, they can look at this and say, okay, if I follow these guidelines, I will get the answer to a certain accuracy. And I can be pretty assured that I'm following the right guidelines and that I'm consistent with the federal standards. And inside the National Geodetic Survey, they develop open projects so you can automate this, so it would do all the processing for you. One key, very important point: guidelines were developed for input from the GNSS users, because the users are the ones that actually produce a coordinate that's going to be used for floodplain mapping, or going to be used for building a building or building a road. Inside the National Geodetic Survey, they provide the framework, the guidelines, and the network. But in reality, the National Geodetic Survey, they actually didn't use most of it. They do use the information to define and the reference, and they establish it. But the surveyors and the engineers are the ones that actually use the product. So we went and we talked to them about it. And one important side note about this is, I had a lot of users that were using the GPS at the time, and they were going out for a couple hours collecting data on one day and then coming back the next day and getting millimeter repeatability. And they kept telling me that I don't need to do all the stuff you're telling me to do. So what I did is I looked at that and I said, well, come back the next day on a different part of the day. And then all of a sudden they were getting 4 or 5 centimeters difference. And this was because of the geometry of the satellites, the atmospheric conditions. And so we worked with the user and I explained to them what it was, so that when we developed the guidelines, all of this became part of the procedures. So they started understanding what was a good practice. Now, today, with a lot of these real-time networks that you have in place, they handle some of the geometry issues and the atmospheric issues. And all of these are getting much better. So guidelines will change and get better as you go on. So why do you follow guidelines? I kind of just talked about it. They help to detect, reduce, and eliminate error sources. Very critical. And this is a federal responsibility in the United States. Make sure that you are performing procedures that help to detect these problems. And if you can't really eliminate them, what can you do to reduce them? Now, guidelines, as I mentioned, are modified as procedures, equipment, and models improve. Guidelines provide the standard operating procedures for others to follow, so they can feel assured that what they do is validated and that they can be trusted. And so that was very important. And this was, you can see, the original ones were 1997 and in 2008. And so the original ellipsoid height guidelines are very old, from 97, and even the orthometric height ones. So NGS, the National Geodetic Survey in the United States, will be updating these as they perform additional studies, better models, better things. Like I said, the real-time networks that are out there, the GPS and the GNSS real-time networks really are eliminating some of the error sources that were originally back when we were doing in the 1990s. So all of these things are helping to improve the process. Geoid models, they're critical to the establishing accurate GNSS-derived orthometric heights, as I mentioned several times. And in the beginning, when we were first using them, and my first GNSS-derived orthometric height survey I did was back in the 80s. But our geoid model, we've said, even over very short distances, 10 to 20 kilometers, was no better than 10 centimeters or at the best. So we weren't getting good, accurate GNSS-derived orthometric heights, but we knew that we could. So once again, it goes back to that simple equation about the orthometric heights, ellipsoid height, the geoid height. Now we got better ellipsoid heights by following guidelines and better models and tools and equipment. Now the geoid height needed to be. So what's a geoid? The definition, basically, it's an equipotential surface of the Earth's gravity field which best fits, in a least square sense, global mean sea level. So I mean, what does that really mean? It's a model, and you're using a lot. You need a lot of gravity, but you don't have an instrument that actually just goes and directly measures the geoid. There's no geoid instrument like there's a leveling instrument or a GPS or GNSS receiver. You don't have a geoid receiver. You can't dig down and see the geoid. I like this cartoon. It's from the Canada. It's a real old one that they put together. That it really shows the geoid affects what's above you, what's below you in the geoid. So everything that you have is affecting the geoid. And that's why it's so complicated. It's not a simple task. Computing a geoid is, as I said, not a simple task. It takes a lot of various types of data. Global digital elevation models, very important to get good, accurate elevation models for trying to say what's the terrain effect, because your geoid's down below your terrain. So what is the gravity value when you reduce it? Local gravity data sets, getting accurate gravity and new gravity data is very critical. And then obviously global gravity data sets, which is probably one of the most important, excuse me, that aspects of what has been created or developed over the years is the global gravity data sets from the satellites, because that helped to give the very long wavelength improvement and reliability that you believe you knew. This is a very complicated diagram. It's really like an eye test, if you will. But I like this because it shows the complexity of what you're doing. It tries to simplify the complexity, but it highlights three different aspects of what you have. You have a global digital elevation model that's important for terrain induced attraction and potential. So you really need that. And it shows that path. And then the blue shows the local gravity observations, which are very important, once again, of getting that local variation. And the more gravity you have, the more you're able to detect changes in the geoid direction, the slope. And then the global gravity coefficients, these give you this long wavelength, which is a reference model. Everything lies on that. So that's extremely important. And the more accurate you can get that foundation, then you can focus more on the local effects of what you have. So once again, this is all documented in a report by Dan Roman at the National Geodetic Survey, and it's out on their website. So building the geoid model, this is a slide I got from the National Geodetic Survey. Satellites, GRACE in particular, the GRACE follow-on missions give you the long wavelength. This gives you the Earth. I mean, the Earth has got a lot of bumps and wiggles in it because of what's inside it. And on top of it, the topography of it, but the density and what's going on inside the Earth and the changes in density. And this long wavelength is very critical. Once again, it's that foundation that everything will land on. Then the intermediate, the National Geodetic Survey is doing airborne measurements with gravity across the United States so that they can get this intermediate wavelength that helps to validate the long wavelength of the satellites, but also in supplements and validates some of the changes between the local gravity, the short wavelength. So the intermediate is important for trying to help with getting the local differences, but the short wavelength is basically surface measurement, surface gravity, as well as predicting gravity from topography, reducing the terrain effects. That is really critical to trying to get, and so you need a lot more gravity information. The long wavelength, once again, GRACE and GRACE follow-on mission, very critical. There's a website out there that anybody's interested in. You can get all this information, and it gets a lot of good products, and they keep improving it and getting more and more accurate values. So pretty amazing technology, very sophisticated, and really important for the long wavelength. The intermediate wavelength in the United States, as I mentioned, is by Farian, and they call it Gravity for the Redefinition of the American Vertical Datum. This program's been underway for about a decade, collecting data, because they knew that they needed to get a better geoid model if you're going to really be able to do GNSS-derived orthometric heights. And this is a status map that I just pulled off the website. Although it says last modified in July, things haven't changed a lot, especially in the flying because of the COVID-19 virus. But you can see the green is data that's available. All the gravity data is available and been included in their geoid models. The blue is being processed. The orange is underway, it says, and the white is planned. But you can see they covered the entire United States, and they're common. They're like Puerto Rico and Guam and Hawaiian Islands are some of them being planned. So all the Commonwealths of the properties so that the geoid model is going to cover a quarter of the world, and they wherever they have this gravity information. But this was a very big deal, and once again, the reason they did that is this airborne gravity provides a higher resolution enhancement to the space phase. So now you got the GRACE and the GRACE follow-on to give you the long wavelength. You start to get this from the airborne to give you the intermediate, and then now you got to get down to the short wavelength. And this is a plot of the terrestrial gravity data that was used in the United States for their latest scientific geoid. And there's a paper out. Once again, you can find this on NGS's website, but this is a paper that defines their gravimetric geoid model of 2019, and it gives a lot of the technical information. What here I want to show is the terrestrial gravity. You can see so much gravity data. The darker it is, the more points you get per kilometer. And you can notice up in Alaska, a lot up here, that's because of the oil, and there's a lot of data that was collected. But all of this information is useful and in part of trying to do the model. Digital elevation data, once again, I mentioned that was very critical, and getting better and better digital elevation models so that you can do terrain corrections and understand the topography, because you take the gravity observation at the surface, but you want to reduce it. So having better digital elevation models are very, very important, and utilizing this information and involving some of the algorithms for terrain corrections helps to get a better short wavelength of the geoid model. So that's a lot of the information, a lot of data that's part of trying to get the scientific geoid. I'm going to talk a little bit about hybrid geoid models. And I got to admit, I don't like the word hybrid geoid model. NGS publishes these, what they're called hybrid geoid models, and they are different than their experimental gravimetric geoid models. Hybrid geoid models are not real geoid models in the United States. There may be other people calling hybrid geoid models in the world, but all the ones I've seen that they call hybrid geoid models, they're really transformation models. They're linking the ellipsoid height system, if you will, with the geoid model to get a orthometric height. So they're linking the two. That allows you to transform an ellipsoid height into the same reference frame of the vertical. In the case of the United States, it allows them to take an NAD 83 2011 ellipsoid height. That's their geometric system, and it allows them to get a GNSS-derived orthometric height reference to NAVD 88, the North American vertical datum of 88. So that simply allows them to take an ellipsoid height and get an orthometric height that's consistent with a leveling-derived height. So it allows them to get a GNSS-derived orthometric height consistent with a leveling-derived orthometric height in the United States. That's what's going on. Now, there's a document out there on NGS's website that talks about the technical details of Geoid 18. And I write some newsletters for the GPS world. And if you go out there and type in my last name, Zilkoski, say GPS World Zilkoski, you will get a list of a lot of these newsletters that I do. And one in particular, I talked about the Geoid 18 model and what was done on that. And I, as a consultant, I was helping NGS in the analysis of their data points, which I'll talk about in a minute. My point being here, though, is there is technical documents of this, and I would encourage people to go look at all these documents, because NGS has done a very excellent job of documenting all of what they're doing, their procedures. So how are hybrid geoid models really generated in the US? Okay, as I mentioned, hybrid geoid models are based on gravimetric geoids. They start with a purely gravimetric geoid. They got the long wavelength, the medium, intermediate, and the short wavelength, and they create a gravimetric geoid. And they say, this is the best geoid value I have. And we believe it truly represents the least squares of the mean sea level, global mean sea level. That's what they're establishing. Now, the hybrid geoid model, once again, is trying to say, hey, if I want to use this geoid model, I need to make it consistent with my current vertical control network in the United States, NAVD88. So if you occupy a benchmark with GNSS receiver, you get a GNSS-derived ellipsoid height. And if you've occupied a benchmark, it already has a leveling-derived height. Then you can compute a geoid height by just taking the ellipsoid height minus the orthometric height. Once you do that, and that's what NGS did, then if you remove some trends and local differences and model it, you can create this geoid, which is called a hybrid geoid, that will be consistent with the current vertical reference, which is the NAVD88. Because the height here, this orthometric height, is the NAVD88. And that's the goal of a hybrid geoid. Once again, you've seen this diagram before. Estimating geoid heights, you're just taking the same equation and moving it around, and you're getting a geoid height now instead of the ellipsoid height. So you got the ellipsoid height that you get from GNSS, you get your orthometric height that you're going to get from leveling, it's already there. You can take the ellipsoid height minus the orthometric height, and that gives you your estimate of your geoid height. Once again, that geoid, that's an estimate of the geoid height that you found based on ellipsoid height and orthometric height. That's going to be different from your gravimetric geoid. And this is inside the United States. There was over 32,000 of these occupations. People went out there, took a GNSS receiver, occupied a benchmark, and they followed certain procedures. Basic concept was occupy them at least twice on different days, different times of the day, and about 4 hours each day, so that you had at least 2 observations that you can check the ellipsoid height, make sure it's good. You can remove any kind of inconsistencies. You can remove some of the systematic effects, average amount, and you got an ellipsoid height. The orthometric height came from leveling data, in this case, the NAVD88, and you estimate the geoid value. So the estimated geoid height is the ellipsoid height minus the orthometric height. Then you had the modeled gravity. And the residual, what we're calling the residual, is your estimated height minus the model. Now, if in fact they were all on the same surface reference, that residual should be 0. But in reality, it's not 0. You have lots of differences between them. First off, your geoid height is based on a certain reference frame. Your ellipsoid height's based on a reference line. The orthometric height's based on a different, and they're all different. So you have to bring in this case, in the United States, they had the NAD 832011 ellipsoid height, the NAVD orthometric height. So you knew that there could easily be a bias and a tilt or differences. So the residual, you had to go in and remove a bias and tilt. Now we had over 32,000 observations that we can look at. That's a lot of data to look at. But each one of these observations were evaluated. We called them residuals. You removed a bias and a tilt first, because we didn't really care about the bias and we didn't really care about the tilt. We knew that between the geoid model, we knew that the leveling data probably had some kind of tilt to it. And we figured there would be a bias because the NAVD data held a local mean sea level value at one station. Well, there's a bias between that station and what is really represented the global mean sea level. So we knew that there'd be a bias, and we saw the tilt, which is probably leveling error. So you remove those. And then relative stations, we looked at stations that were 2 centimeters in less than 5 kilometers, because we felt that the ellipsoid heights were good relative over short distances, and the geoid height or the leveling height should be good. So if we had a problem, we knew that most likely in this very small differences, that it was probably a bad orthometric height because it may have moved since the last time it was leveled, or the ellipsoid height was not that good because some of these ellipsoid heights were done 20 years ago when the procedures and processes weren't as good. But point being here, all of these observations were looked at and analyzed before going in. And this is out of their publication, NGS's publication, and they call it a geoid. And notice it says conversion surface, but that's basically what the hybrid geoid does. It gives you a conversion surface. This is a diagram showing after geoid 18, the hybrid geoid was made. This is the hybrid geoid minus the computed ones. Now remember, the computed GPS on the benchmarks went into the solution for the hybrid geoid model. And this is these values right here are plus or minus about 2 centimeters. And you can see most of the values are within this plus or minus 2 centimeters. But you got some highlighted values that are very large. And in reality, not that large, but some subsidence are 8 to 10 centimeters. So you do see some of these differences. Some of that's due to movement. Some of it's due to the leveling network having, the NVDA leveling network having some errors. Some of it's due to the ellipsoid heights, lack of information in the area. We don't know. But all in all, it basically fit to a couple centimeters. And that's basically what the statistics are showing. The minimum max was about inside the United States in what's called the CONUS, the lower 48 of what I just was showing the diagram of, 10 centimeters and a maximum of 8 centimeters. But the standard deviation was 1.27 centimeters. So overall, all in all, it fit very well, meaning that we removed a lot of the outliers. There are some outliers that are there, but we tried to remove that. So this is the first step of trying to create a geoid, a hybrid geoid model that allows you to be consistent. So you could go out and occupy a station with a GPS or GNSS station, apply the geoid model, and be pretty certain that you're consistent with the NAVD88. Okay. So now this is that conversion surface. So what does it really show? It represents the difference between the 88 and the geopotential gravimetric. So all these things, you see that there's a tilt that's going through there. There's a bias that was in it. And all these little bumps, you can see fine detail. All of these are representative of all because of having over 32,000 observations inside here. So we had a lot of information. And where you see a lot of different structure, meaning we probably had a lot more data in there. So the difference between the hybrid geoid and gravimetric geoid in this case is the geoid 18 is a hybrid, and this is the scientific geoid. So this is what was modified. Basically, the hybrid geoid creates a surface that'll take and modify the hybrid, the gravimetric geoid, so that you can use it to get an NAVD88 height. And as I mentioned before, it had a bias, a tilt, and some local warping between benchmarks. And it is warping. It was made to conform. So if the leveling height was bad or the ellipsoid height was bad, that we missed it in the analysis, it's been warped. But that's the change you'd have. So you change the geoid value so that it would be consistent. So if I went out and I occupied a station here with GNSS and I applied this geoid model, I would get close to the NAVD88 height. That was the goal. Now, the last part of this is defining the future reference. You have to relate this new reference frame to the old reference frame. And so now you readjusted your vertical control network so that you have the best possible vertical data. You've established guidelines for the ellipsoid heights. You developed a better geoid model. And so now people can actually trust what they can get from a GNSS-derived orthometric height that is fairly accurate and consistent. Now, what are you going to do in the future? These are documents that NGS, and you go on their website and you can get them. There's 3 different documents. They talk about the geometric change to the network. They talk about the geopotential change, which is the vertical part. And then how are you going to work in this? Because this is going to be a time-dependent system. So one is talking about replacing the geometric part, the NAD83. One is talking about replacing the vertical, the geopotential, the NAD88. And the other was talking about how are you going to utilize these? They're improving their tools, better surveying methodology. All of these are coming in. So they're trying to document. My point being here is they are creating these documents to try to do that. So what do you have here? You have 4 geometric ones, what they're calling NatRef, CatRef, PatRef, and MatRef. But anyways, what it is coordinates are changing because they're located on tectonic plates. And you can see that there are 4 basic plates for what the US is responsible for. So they have created these different reference frames because they know that they're moving. Major tectonic plates, you have the 4 different ones I talked about, and you can see NatRef. So this little diagram showing the plates are moving, so coordinates are moving, and you have to take into account time. So at a certain epoch, you have a value. That value is going to change. National Geodetic Survey is going to have a time-dependent component. They will always have someone being able to go back to a reference epoch. In the case that they're talking about, maybe 2020.0. But when you process data in the new system, you're going to get a coordinate for that day based on the movement. And then they will move it back to this epoch coordinate. That's a new paradigm of how things are done. Parts of it will be transparent to the user, but it will give a new based on movement. Now I'm going to talk just briefly about their one blueprint number 3, which is geopotential coordinates, because this is the transition. This is going from a leveling drive to a purely the GNSS-derived heights. I did a GPS World newsletter. Once again, it was in one of my newsletters that talks about this, what they call NAPGD 2022, North American Pacific Geopotential Datum. NAPGD 2022, you know, it talks about the global potential model, the GravD that we talked about, the geoid model, which is critical. But this article talks about it. So, but I'm just going to highlight briefly, what's a geopotential datum? It provides, under one umbrella, it provides a geoid undulation, so you need that geoid height. Acceleration of gravity, you're going to need gravity. If you're going to do leveling, you always need to incorporate gravity to reduce those observations to geopotential differences, do an adjustment, or get a potential number, and then compute an orthometric height with gravity. In the case of National Geodetic Survey and NABD88, they used a Helmert height, but they needed the gravity value. So the same thing will happen if you're going to incorporate leveling data into this new geopotential data. And it does a geopotential number, the deflection of the vertical. So any latitude, longitude, and height, or any latitude, longitude, ellipsoid height, and time will be it. So it's time dependent, but that's what this geopotential data will provide. And very simply, it's what they're going to call a global Earth global geopotential field. We're going to have a regional gridded geoid undulation, deflection of the vertical for people that still want to use it. And then they'll have this gridded surface gravity data, all of this under one umbrella, and it all be time dependent. Although the gravity in the geoid model is not going to be changed as much as the geometric part of this, but it will be incorporated, and they've already started doing this. A new paradigm for people, new surveyors. Once again, in the United States, all of their models and tools will be in the background, and so users will be able to select, do they want the current coordinate of today, or do they want it referenced back to a certain reference epoch, which most surveyors will use a reference epoch. I did this in one of my GPS World, but it's an approximate change between what it is the surveyors are asking, well, what's it going to do? And you've seen this diagram before. All of this is based on the GPS on benchmarks, but you'll see that there's significant differences between the the future reference datum and NAVD88, starting basically flat 0 near Florida, which is just coincidence, all the way up to over 1 meter in the state of Washington in the west. But clearly the systematic tilt and the bias is there. These are the differences. Not for surveyors, it's not an insurmountable task, but it will be an issue that all products and services need to be looked at. Everything will be changing. And this is part of what NGS is working with the users now to say, well, once you do this change, what is the impact? So NGS has a lot of these documents now. They have a lot of this information. And because of everybody occupying all these benchmarks, they now know what the change will be and how they can influence, how they can do it. So what's the really bottom line? And I've said this several times. The new paradigm shift is that the users won't have to do a lot of leveling. They will still want to do some leveling, but to access in the United States, the National Spatial Reference System, you will need to use GNSS receiver to get an ellipsoid height. You'll use the global model to get a geoid height, and then that GNSS-derived orthometric height, which you're going to call this NAPG, North American Pacific Geopotential Datum of 2022, that will give you your GNSS-derived orthometric height that will be used. So they have, for the user, in this example, if you're in, say where I live in North Carolina, you will have an ellipsoid height. You set up your receiver, you'll submit the data to the National Geodetic Survey. They will give you back an ellipsoid height, a geoid model value consistent with that ellipsoid height. And the end result is you will end up with a GNSS-derived orthometric height that is consistent with the ellipsoid height in the latest new reference frame. That is all of this. That's all the process. Now, leveling data will be allowed to be incorporated into it using the gravity, and they will have procedures for doing that. For the most part, anybody that's going to do any kind of control, they will be using GNSS-derived orthometric heights, this system. Just showing a very simple diagram, once again highlighting the fact that this ellipsoid height comes from inside. If you occupy a station, you can get this ellipsoid height, you'll get this geoid height, it will give you this orthometric height. It is time dependent if the geoid model is changing, but once again, it will be able to get users to the time epoch that they're asking for. It will give them today's orthometric height and also a process to get it back to the reference epoch. In the case of National Geodetic Survey, looks like they're going to pick on 2020.0. Now everything is relative, and so users are interested in relative height differences, and so NGS is looking into trying to say how accurate can they get this. They know they'll have ellipsoid height differences, the geoid height differences, and so some of these areas will drop out, and they believe they can get this orthometric height done to better than 2 centimeters, which is their goal, which is very reasonable to be able to do. So in summary, went over this. I know this was fairly quick, but I've tried to bring a lot of references so that you're able to go back and obtain it, give you highlights. We ensured that in the National Geodetic Survey, they ensured that the latest for control was consistent and accurate. So they had a good foundation to start with, rather than knowing that the leveling-derived heights weren't. They needed this. Then they developed guidelines and products for estimating accurate GNSS-derived heights, ellipsoid heights, and then the orthometric heights. They did this so that the user can get transition from leveling-derived to GNSS-derived. And it's happening inside the US. And the last bit is the redefine the vertical reference frame and its relationship. They created these documents that describe what they're doing, their process, how they're doing it. They are doing all of those so that they're able to explain to the user what they're doing, and more important, getting user feedback early on so they can look and say, well, what is the impact? How are they going to transition? What kind of tools do I need to do? So NGS is doing all of that and trying to make that happen. One final thought, and this is from a very intelligent individual, at least he believes in intelligence. He's my brother. He's a medical doctor in Montana. And he told me once, if you geodesists did it correctly the first time, you wouldn't have to keep performing adjustments and changing the value. Just do it right the first time. So my answer to my brother was, my response, life is a continuous process of adjustment. Gandhi said this, and life is changing constantly. I love change. I love the analysis. I love being able to get to that next level. And so the next level of geodesists, the next generation of geodesists are going to improve it even more. I want you all to realize geodesy provides a foundation for all geospatial products and services. All. If you don't have geodesy involved with trying to do it, you're going to have issues and problems. This is why, in my opinion, we need more geodesists, more trained. We need them looking to the future, improving the process, all the algorithms. I remember when I was at Ohio State in 1979, we were watching and processing Doppler data at a Doppler receiver, and you basically babysat this Doppler, but you sat there overnight and let this thing run and go. And now you can go out with a GPS receiver with some of these real-time networks, and in minutes and seconds, actually, you can get a more accurate height, coordinate, latitude, longitude, ellipse height, and now orthometric height than we could in 1979, sitting there for days. So what's going on in the future? That's where you all come in to be able to go to that next level and find out what it is and have a lot of fun. I've had fun my whole career. I appreciate the everything that allowing me to talk to you, because I love geodesy. Been doing it for, like I said, over 45 years, and I'll continue to do it. So I appreciate it. Thank you very much.
Wow, thank you very much to you, Mr. Dave. You did an excellent presentation. It was absolutely awesome. Seriously, thank you very much for sharing with us all your knowledge and everything that you have done in the USA. Really, thank you very much. And right now, I'm going to read some questions for you so you can answer. Okay, the first question is asked by Hermógenes Suarez. He asks, will the current geoid model, geoid 18, replace in the NATRF 2022 will be implemented?
Well, I think I understand the question. In when they do the new reference frame using the ITRF 14, they will be using the latest geoid model. In this case, they have one called geoid Geoid 20, and so that will be consistent with National Geodetic Survey will not do another hybrid geoid model. They will, the geoid 18 is the last for connecting to the NAVD88. But after they do what's called NatRef, after they do the geometric and they get all these ITRF reference, then they will have the latest geoid model. Right now it's geoid 20, Geoid 20, and they will have a transformation surface that will take people from the new reference to the old NAVD88. So yes, they will create a new transformation. They won't call it a hybrid geoid. What they'll call it is some kind of transformation tool, getting back to what it really is. So yes, they will create this once they establish finalize it to ITRF. And it will, right now it's ITRF 14, but ITRF 20 will come out 2020. And so they'll probably update it for that if in fact they have time to reprocess all of their continuous operating reference stations. I think I answered that.
Okay, the next question is by Jose Beltran Vasquez. He says, we need to know that GNSS is not good for elevations. That depends about the elevation model, which is the most accuracy.
Oop, did I lose you?
Okay, he asks, we need to know that GNS is not good for elevations. That depends about the elevation. Which is the most accuracy in this moment?
The ellipsoid heights, I think I understand the question. The GNSS-derived ellipsoid heights are probably the most accurate. If they, depending on how you do it, you can get it easily to 2 centimeter or better. The geoid height is probably, in an absolute sense, the geoid height's probably got a larger error, but the relative sense, the geoid height, say you're going 10 kilometers, that geoid height error is probably millimeters. So the ellipsoid height becomes the limiting factor. But as you get farther and farther away, the ellipsoid height itself, its accuracy doesn't really change. It's still pretty accurate. Then the errors in the geoid height become. So it's not a very simple answer. It depends on your starting station to the other one. In other words, where between one station to the next, what it is. So when the relative difference, the ellipsoid height's the limiting factor. In an absolute sense, probably the geoid height. I'm not sure I answered the question, but I think that's what he was saying.
Okay, he also says, what is the situation outside of the United States and Canada about geoidal models?
That's a good question. The United States and Canada, the National Geodetic Survey and the Geodetic Survey of Canada are collaborating and developing one geoid model. So their geoid model will be between the two countries. There will be consistency. They're working on trying to create that, and they're also working on the definition of where they say this is basically the zero geopotential number. They're sort of basically saying they're in the definition of all of their data. They're collaborating so that they do have basically one North American geopotential model. That's what their goal is. And so they meet, as far as I know, we used to, when I was there, meet a couple times a year. So they have these periodic meetings and they have a working group to try to ensure that they can come to an agreement. As with any scientists, they have their own opinion about how certain things should happen. So they're working on some of these differences of processes and stuff. But the goal is to be one geoid that goes by the border. Same thing in where you'd have in Mexico with the United States. Good question.
Okay, next question is by Juan Quilaleo. He says, what do you think about EGM 2020 for South America?
Well, I'm not sure I can answer that for South America and so forth. I think what you need to do anybody needs to do when you get that, you need to validate the model and see how good it is in that particular area. Because remember, all of these things depend on the data that goes into them and the processes, and each locale is different. So it all depends on what data goes into that process analysis. So what I would say is, the first thing is, you would say, depending on your area, you would try to evaluate that and say how good it is. I mean, I couldn't tell you what it is until you really get some additional data to kind of validate what it is. Just like in what the National Geodetic Survey did by occupying all these benchmarks that had good ellipsoid heights, they tried to validate and they used this information. So that would be what you'd have to try to do to determine how good it is.
Okay, next we have a comment from Bruno Blanco. He says, greetings to all participants from the UMSA career of Geodesy, Land Surveying, and Geomatics from La Paz, Bolivia. Greetings, Bruno. Thank you for being here. Now we have a question from Laura Sanchez. She says, slide 44, when you mention time, should coordinates, orthometric heights, geopotential numbers, and reference surface, GEOI, be time dependent or only the coordinates? If coordinates and GEOI should be time dependent, how can we separate the variation of each one? I mean, how much of the potential change corresponds to the orthometric height and how much to the GEOI?
That's an excellent question. And I'm going to say, I don't think you can separate some of it. But so let me address some of what's going on and what the United States is doing. The time dependent for the coordinates of the latitude, the longitude, and the ellipsoid height, they're all being based on the movement of the plates, and they'll have what they call like a shift and drift. They're going to use all of these. They have continuously operating reference stations, what they call cores, and there's a couple thousand in the United States, and they're going to use that information to make models for the movement with inside the plate. In other words, they'll use the plate movement and the rotation that IGS creates, so you have some variations that are going on, but then within the plate, they're going to use all this local information to identify that. And in the geoid model, they are looking at utilizing all the satellite information that are telling you have changes in the geoid, like Grace and Grace follow-on, looking for these large, and it takes large mass changes to change the geoid. You got a sea level rise, which is changing the geoid. So they're utilizing that to create what they believe the geoid model change is, totally independent of the actual values that you're seeing when you use GNSS. So they kind of independently say that based on some of this other information, and that's how they're going to get the time-dependent geoid model. And the geoid model is going to change very, very little year by year, but over 30, 40, 50 years, it will change. So they're kind of building in. But I would suspect in most areas in the United States, it will be small. But if you get into Alaska and into Canada, where you have a lot of post-glacial rebound, where you have actually the land changing, so now you got a change in the height due to just the movement, but the geoid's also changing because of the change in the geology. So they're trying to determine how to separate it, but I think in the end, it's going to be very difficult to really say that it's a height change or it's a geoid change. And the geoid, like I said, is going to come from the independent observation from satellites and gravity observations. They'll do gravity observations, and then they'll do absolute relative gravity observations, absolute gravity observations, and use the satellites. But a change in elevation will definitely change that information. So that's an excellent question, and I'm not sure that they have an exact way of separating it yet, because it's a very small number.
A comment from Douglas Bravo. He says, good morning, excellent presentation, a great contribution to geodesy in America. Greetings from Venezuela.
Well, thank you.
We have a question from Antonio Marquez, I think. He says, how will be the relations with the absolute high reference frame? Will it be consistent?
Yeah, once the new reference frame is established, and they have what's called this, like say NatRef, the North American Terrestrial Reference Frame. So once that's established, that ellipsoid, the latitude, longitude, ellipsoid height will be consistent with the geoid height. So they'll be part of the same system. So when you apply them, you're going to get this orthometric height, which will be called the North American Geopotential Reference or Geopotential Datum, North American Pacific Geopotential Datum. So that GNSS-derived orthometric height will be consistent with all of the rest of the heights when people are established. Now remember, the old heights that were in NAVD88, if someone wanted to compare the new height in a new system to the old one, that's what they'll use this transformation model. There will be a transformation model to take you from the new system back to the old, so that you can look at old products and services and say, well, what would it be? So if I say I went out, say I had a topographic map and I wanted to build something, but I wanted to get a new elevation, I would go and occupy it, and I would get a height in this NAPGD2022, but all my products are in NAVD88. You would run this transformation tool to get that new value into the same NAVD88 system. And similarly, if you had an NAVD88 system and you wanted to say, well, what's it in the new system, you would run this transformation tool. So they are going to be different systems, but it will be all intertwined through models and tools.
Okay, next comment is from Marcelo Kisbert. He says, good morning, good presentation. Greetings, Dr. Davud Zilkoski from Bolivia.
Well, appreciate it.
There is another comment from Anna CMC. She says, good morning, I have a question. Why don't you use gravity modeling for the transformation?
Well, let's see. You in the transformation, you start with the foundation is the gravity model of, so you have the gravity model creates the geoid model. So your transformation, you start with a geoid model, and the transformation really is changing the gravimetric geoid model so that you remove the bias and tilt, because the gravity model is not in the same reference system as the current vertical model. So there's two different reference systems. And so the transformation model takes the reference frame of the gravity model and the reference frame of the NAVD88, and that transformation model removes the bias and trend, and then some of the local warping and differences. So you need to start with the gravimetric geoid model, purely gravimetric, to transform it into, so it's into the current NAVD88 system. But basically, because they are not from the same reference surface, there's a bias difference. The gravimetric model picks a certain value and it says, this is my zero surface, I'm starting point, this is what I'm saying it is. And it's different than the NAVD88. So you have to apply a bias to get the system to bring it up to it. And then, as I showed in my diagram, there was a tilt between the gravimetrically derived geoid model and the leveling values. There was a tilt between the two. So you have to remove that. So that's basically why you want to start. But I guess the bottom line is just different reference frames. You have to bring them together.
Okay, thank you very much. We have the two last questions. I'm sorry, the three. There is a question from Juan Shewat. He says, with the use of the new altimetry models, what precision would the low accuracy GPS have?
Repeat the question one more time, I'm sorry.
Yes, of course. This question is from Juan Shewat. He asks, with the use of the new altimetry models, what precision would the low accuracy GPS have?
So if I understand the question, the goal is to get it better than 2 centimeters for the GNSS-derived orthometric height. And so the ellipsoid height is probably, they're trying to get it to better than 1.5 centimeters, and the geoid height better than 0.5 centimeter. So you would be, the goal is to get it better than 2 centimeters. And so 2 stations next to each other may not meet like the accuracy of a level you need, but the farther and farther you get away, you still have that about that 2 centimeters. So that's the goal right now. That's why leveling is still important to people that need to get down to the millimeter range. You still need that. Although I leave it to the future geodesists to improve algorithms and models to be able to remove some of those, like these real-time networks that remove the errors associated with the geometry of the satellites and the atmospheric conditions. You now can get very, very accurate ellipsoid heights in a short period of time. There'll be better improved models in the geoid heights so that we can get that to this better than the centimeter level. But right now, I think it'd be 2 centimeters.
Okay, we have a question from Hermes Garcia. He says, excellent presentation. Congratulations. Do you consider practical migrating to a GNSS-Derived height with hybrid geoid models in countries with a considerate amount of tectonic movement like Chile?
Yeah, that's an excellent question, because you have a lot of motion, and you need to be able to account for the motion. But to get to that, you probably need to do something similar to what the US did. You need to say, okay, I got my current vertical network, and you have a lot of motion. So your current vertical network probably isn't that good because of the motion, but you're using it. So I would say you want to try to look at the current vertical network. You want to occupy it as much as you can. Because you have movement, you need to do it almost in a snapshot. You need to get out there and do it in a timely manner, such that you can say, hey, here's what we believe the GNSS-derived ellipsoid heights are today, and here's what the leveled heights are published, and start looking at the differences. And that would be your first approximation of like a hybrid geoid model. But because if you have old leveling data and you had crusted movement, which you do, then you don't know, when it happened. So in the case of that, you need to almost potentially do some leveling in areas where you have a lot of movement. And I wrote a paper on one thing about in crusted movement areas that you don't need to level 1,000 kilometers. What you do need to do is you need to go in an area, say you got a city, and maybe you got to do some leveling, current leveling, say 20, 30 kilometers, and do some GPS in that same area. And now all of a sudden you can evaluate your local differences. And now you have a good indication of what the geoid model is, and you can create a hybrid geoid model that basically is local. It's not ideal, but it's local. And then you can build on that. But if you have movement, you got to keep modeling that movement. Like in the United States, California is moving. Southern California is moving, but they have hundreds of GPS receivers that are called cores that have been modeling the movement. So every day that they go out, they get a coordinate that's based on all this movement. I don't know how much are in Chile. I do know that a lot of, I know some of my friends at Ohio State have gone out there, put in these long-term receivers so that you can detect the movement and model it. So I would say you'd start with looking at how many GPS receivers you have, their GNSS receivers really, and how, if they're recording information, then what's going on, and you can have coordinates in movement and velocity information. Once you got an earthquake, then you got to start over and do it again. But if you start with that and you do some leveling, then you can create a good hybrid geoid. But if you don't know, if the leveling is no good, then you're just, you're just modeling the movement, and that may or may not be good. But if that's what you're using today and you have it and you got movement, then at least it would be the first step of trying to get people utilizing the satellite information. Yeah, that's a, without having a lot more information, I don't know if I can say anything more about that.
Okay, and the final question is by Anthony Prince. He says, greetings, Dave from Venezuela. Excellent presentation. When calculating heights in differential mode, is the standard accuracy 2 centimeters? Gilling's plate 11. Which elements are the most important?
Yeah, in a differential mode, the ellipsoid height becomes the most important, because the geoid height over relatively short distances is probably more accurate than the ellipsoid height over the short distances. So it's really doing an excellent job on the ellipsoid height. Say you're going 10 to 20 kilometers, your geoid height difference is probably good. It's much better than, I mean, it's below definitely below the centimeter level and probably into the millimeter level. But the ellipsoid height, you need to really work on getting that accurate. That would be your limited factor.
Okay, we have finished with all the questions. Before finishing the conference, I would like to thank you, Mr. Day, for your time, for talking about your experience and the works that you have done. It is really important for us to know more about how these work in the USA. And right now, I'm going to show you something. Just give me a moment. Just give me a second. Okay, just give me a little bit. Okay, here is. Okay, I'm going to share it. Okay. Please let me know if you can see it.
Not yet.
We want to give you a certificate of recognition from the AAPG UCB Student Chapter and AAPG Young Professionals Venezuela Chapter. So if you can see the certificate, I don't know if you can see it now.
No, oh, there it is. I got it. All right, looks nice.
Okay, so here is a certificate from us. I'm going to read it. Certificate of recognition awarded to Davud Zilkoski for presenting the talk, the process of transitioning from a National Leveling-Derived Height System to a GNSS-Derived Height System. I'm going to send it to you to your email. And once again, I wanted to thank you for taking your time with us, teaching us new things and sharing with us all your experience. It was an excellent presentation and thank you very much for being here. Hopefully next year we will still have more activities about geodesy. We would like to invite you.
Well, I appreciate, you letting me give my little spiel, and I enjoy this, and good luck to everybody. And once again, just remember, like I said, the Odyssey, it's the foundation. Don't let anybody tell you it's not.
Exactly. And thank you very much to all the participants who are here, who were here with us. Thank you very much, everybody. And so tomorrow we will see again in our Geodesy conference. Thank you very much. Have a good afternoon, and we will see in the next conference. Thank you very much all.
Thank you to everybody else. Thanks.